So we finished talking about this set of slides on internetworking last week, right? And I had given you some mini homework, right? So one was this. So anyone want to share? How did I get this 5 in 10,000? Do you guys think about it? No. Did you think about it? No? Okay. Okay, so let's come to an understanding. I'm going to ask you to do things. All right, so I expect you to write them down. So I actually asked you to do 3 things last week. This is just to remind you. One was this. Second was to read, there was a article on cross-layer design. And the third was to install Wireshark. Okay? So I hope that this is an okay way of doing things where I ask you to do something. My expectation is that you do it, okay? So let's try. Okay, it's quite simple. There's a reason that I ask you to do it. It's to help you understand. Right? So this is not a probability class, but this class relies on probability. So for example here, right? So if you think, for example, that you're having trouble doing this, this should be a sign for you that you need to brush up on your probability. All right? So remember, it's not about knowing probability so I can solve a problem. Right? A lot of the concepts are probabilistic, so you won't be able to understand things if you don't have a decent grasp of probability. So this was, as I mentioned to you, pretty simple exercise in probability. Just basically counting. Let me see, I was going to... Okay. All right, good. So don't worry, there's stuff written on this, but... okay, so we want to look at... so remember, we want to compute the probability, right? That what? So remember, we had a statistical multiplexing system where we let in a bunch of users. Each user is active only 10% of the time. So this is nothing but simple sort of like, this is almost like a coin tossing experiment. Okay? So all we need to do is to count what is the probability that since we have only, so remember the setup was that there's sort of 10 pieces of resource and we're going to allocate them opportunistically, right? So we have 10 kind of pieces of pie. Each user wants a piece of pie. And if 11 users want a piece of pie, we have a problem. So I want to compute what's the probability. So the problem is that the system will fail. We want to compute what's the probability that the system will fail. Right, so what's the probability of failure? So the probability of failure is just a probability that the number of users is what? Sorry? 11 or larger. So I'm going to say this is greater than 10. Okay, I didn't say greater than or equal to. It's greater than, so that's 10. It's 11 or above, exactly. So now, at this point, all I have to do is figure out what is the probability that there's 11 users plus probably the 12 users and so on, all the way up to 35, right? But let's say we're a little bit lazy. We want to count less. So this is just a probability, or it's 1 minus the probability that the number of users is what? What? This is what? Yeah, less than or equal to 10. So now all we need to do is to compute the probability that there are k users. Right? So what is the probability? Now, assuming these users are independent, what's the probability that there are k users? Do you know? You were shaking your head, so I'll ask you. Yeah. No, 35 is the total number of users. And I want to know what is the probability that k users are active. So this is that the number of users, right? So a user is active. 35 is the population of potential users. So what's the probability that k users, let's say, are active? What is it? Do you know or not? Okay. So you think back to the problem. We had that users is active 10% of the time. Right? So what's the probability that k users are active? Huh? So for example, let P equal probability of user being active, okay? So P. Okay, so can we now write this in terms of P? Yeah, is what? A bit louder? P power to what? Yeah. P to the K. Now, if K users are active, how many users are not active? That's what you're trying to figure out. So how many users are not active? Yeah, 35 minus K. And with what probability are they not active? Right? To the 35 minus K. So is this the probability? No. Yeah, because this is a choice of k users. But then the question is given 35 users, how many choices of k users are there? That's a combinatorial question. So this whole thing is multiplied by 35 choose k. Okay? So that's it, right? And then this, so then the probability of failure is just a summation from 1 to what? 1 to 10 of probability of I users. Right? And where this quantity is just here. Okay? And then, does anybody remember what 35 choose k is? Do you remember? Or maybe thank you for answering. The guys in the back, the gentleman in the back. What's 35 choose k? Do you remember or not? You can say yes or no. Yes or no? No. You can speak to me. Otherwise, I'm going to make you move in front. Yes or no? What? You're shaking your head. I want to hear you. Okay. So who knows? Do you just memorize that? Yeah, it is. But yeah, I think you agree with him. Oh, okay. He said the right formula, so I agree with him. But I'm always amazed that when in doing this, people get confused and they memorize. So let me just share an idea with you. Like this says what? It says I have k places, right? And I have a population of 35, and I need to pick k of them. So think of k places. Think of k like chairs. Okay. So how many options for the first chair? Yeah. And how many options for the second chair? Right? And we're going to multiply it, right? Because for every option of like one chair, there are a whole bunch of options for the next chair. So we're multiplying everything. So 35 times 34 up, and I'm going to keep doing this. How many for the third chair? 30 what? 33, right? Up to what? 33. Up to what? Well, I have k seats. Okay, so how many, so I'm going to do what? 35 minus k. Is it plus 1? I always forget this. Is it plus 1 or not? Yeah, you need k terms. So you have to make sure there are k terms. Okay? So that's it. And then, so am I done? Do I care? So what don't I care about? The order, right? So how many ways can you order k things? K factorial. So that's it. No need to memorize. Yes, is what you said equal this? Because it's what? It's 35 factorial over 35 minus k factorial. And a whole bunch of terms cancel, and you're left with this, divided by k factorial. So you don't need to memorize this, okay? You just remember how to do it once, and anytime you need to redo it, it takes like a second in your brain. Okay? I find that students get tripped up on this. They always memorize. Okay? And this simple example, like I showed you how to do it, it applies to a lot of things. It in fact applies even to solving this whole problem. So I hope that you get into the habit not of memorizing things, but of figuring out some fundamental things, and then you don't have to memorize it. Once you know how to do it yourself, your brain will reconstruct it when you need it. You just have to recognize it. Right? The hard part is not remembering it or reconstructing it. The hard part is recognizing, oh, it's just that thing that I knew from before. All right? Okay. So anyway, that's it. If you go and you compute this, I'm not going to compute this right now because it takes some computation. But if you go implement this in MATLAB or even Excel or whatever, you should get the 5 in 10,000. I think it's an approximation, but you should get approximately that. Okay, are we good? So simple probability, right? But you know, a lot of engineering relies on probability. So if you haven't, please brush up your probability skills. Okay, go review. And I think I've uploaded some, if not, I can upload a probability review, but I think you can find. Just go look at a standard probability text. Okay, if you need a pointer, just let me know. All right, so this was one. I wanted to follow up on that. So there's two more things I want to do to wrap up. One is talk about, so another question that I asked you to think about last week was, and we started that discussion last Monday. I was going to share something on Wednesday, but I think I didn't have time. But this was about why do we have MAC and IP addresses? Okay, so let's talk about that. Okay, so what I want to do is ask a series of questions. Okay? So I created this sort of, let's see, it's okay. You can, or I can maybe make it huge so you can't see everything. Okay, let's start with that, okay? Oh, I don't know why there's a 1 there. Okay, so the question that I asked you was, why do we have MAC addresses and IP addresses, meaning why do we use MAC addresses and IP addresses in the current internet protocol stack? Right? So that's the question. Now, MAC addresses are what layer? Yeah, okay, so everybody, what layer are MAC addresses? 2, right? Layer 2. And IP addresses are what layer? Layer 3. So it's okay. This is the third time. I'm going to cut you a bit of slack, but I expect some engagement, okay? If it's too easy for you, good. I'm going to make it much harder. All right? So don't worry about it. But if it's too hard for you, then come talk to me. Participate in the easy questions and learn about the hard questions. Either way, please start to engage. So we're asking about why do we have layer 2, layer 3 addresses? And the first question I want to ask you is, do we need? Now, the thing to keep in mind is that I didn't write it here, but I'm going to write it now. Both MAC and IP addresses are unique. Okay, the MAC address is burned in by the manufacturer at manufacturer time. So, TSMC, when they're making their Ethernet chip, they're burning in the MAC address. Okay? What about IP addresses? Are IP addresses unique? Yes or no? Globally not. Meaning what? Like why? Okay, so globally not, and something to do with IPv4 shortage and local area network, right? So you're almost there, but not quite. Almost. So it seems like IP addresses are not unique, because you can change, right? You can go connect. You can go to a mall, sign up with wireless at SG, get an IP address. You can come here, get an IP address. Go home, get an IP address. Right? So it seems like IP addresses are not unique. Right? Well, all it means is that your IP address, let's say the instantaneous IP address of your device is not unique. But the fact is, in a connected network, you must have a unique IP address. Now, your point about what you call local area network and so on is what you really mean is that I think you mean something like the network you have at home. Your home network or the private network that you connect to when you're at NUS.
Basically on the router, the network, even cross the network bridge, the IP address.
Yeah, but actually across a router it also has to be unique. Okay?
So how the router translates that? I mean,
yeah, a translation is not a routing function. That's an extra thing that is implemented to do what you are talking about. Okay? So it's not part of routing. So in a connected network, you need unique addresses. What's the implication? The implication is that the private network is not connected to the internet. It's actually not. Your home network is not connected to the internet. Meaning, if you draw a connected graph, it's not connected. You have to build some mechanisms to allow you to, for example, surf the web from inside NUS. But there's something needs to be done. Okay, and that's what you talked about, network address translation. But in a connected network, you need unique addresses. So if both MAC and IP addresses, and so IP addresses actually are unique at any given point in time. If you take a snapshot of a connected network, you have unique IP addresses. Okay? You will not be able to find a situation where two nodes have the same IP address in a connected network. Okay? If there's a path between them, then the two addresses have to be unique, have to be different. Okay? So I want you to think about point 2, okay? MAC addresses are unique. IP addresses at any given point in time are unique, which means we can do away with dynamic IP addresses, because I only care about at a point in time. So we assume that there's no DHCP and you're not moving around. Okay, so any point in time your IP address is unique. So both addresses are unique. So the question is, do we need both? So what do you think? So do we need both MAC and IP to build a computer network? So that's the question. And I think so I do ask this question. Okay, so in answering this question of do we need both, we have to ask how many addresses do we need? Like how many addressing system does a information delivery system need? What do you think? Like I think I mentioned this last time. How many addresses do you have at home? Like what does the post office need to send you a message? Yeah? Post office? You guys tell me, come. Why I'm getting dead silence? How many addresses? This could be much faster if you work with me. Okay? I like it's not about the answer. It's about a thought process. So I'm taking you through a thought process. Okay? So how many addresses do you need to build a computer network? You need one. In the same way that the post office needs one address. Your house has one address. You need one. And so if you need only one unique addressing mechanism, it should be kind of interesting that we use two. Right? You have a question? You want to ask your question? Okay. All right, so yes, so we need one. Right? So we established we need one addressing mechanism, and we have two unique addressing mechanisms, right? So yeah, this is just repeating. So in a connected network, point 6, like every host destination must have at least one unique address. Okay, and so the question then, so this means what? We can build an internet with just IP addresses. It means we can build an internet with just MAC addresses. So you have to convince yourself that this is true. Okay, you can build the internet with IP addresses or with MAC addresses. That means you don't need both. All right, so now the next thing I think that will help you is which one is better? If you have access to both, and I allow you to only use one, which one are you going to use? MAC or IP? Sorry, I didn't hear that. I said what? It depends. So it depends on what? Yeah, it depends on what? Good. So somebody was listening to me. Thank you. Who was the one who said that? I didn't quite. Oh, hi. Yeah, okay. So it depends. It depends on what? Yeah, on the performance metric, which could be the range of communication. But let's say we are wired, so range doesn't matter so much. But you're right, it depends on my performance metric. So let's say that my performance metric is complexity. Okay, I'm interested in looking at how complex it is to build these two networks. So in that context, so thank you for that. In that context, which one's better? MAC or IP? Okay, somebody said MAC. Okay, and so I'm going to ask all of you to make a decision. So you must raise your hand to one of these two, MAC or IP. So tell me your name. Huh? Sean. Sean said MAC. Who agrees with Sean? Raise your hand. You don't have to agree with him just because you're next to him. Oh, you agree with him? Okay. Okay, that means who says IP? Okay, so looks like at least from the crowd point of view, Mac wins. Right? Either or Sean, you're really popular. Yeah, so the thing that you have to do is look at what are the properties of these addresses. Now, MAC addresses are burned in by the manufacturer. So TSMC is in Taiwan. They're making Ethernet chips. They're given a block of addresses, right? Some international body has given them a block of addresses, has given all the manufacturers a block of MAC addresses. So TSMC has a bunch of MAC addresses. And they burn them into their chips, and then they ship their chips out. Or this bunch of chips goes to Europe, this goes to US, this goes to Singapore. Do you think MAC addresses have any structure? Why? You say yes, he says no. Because TSMC is just shipping them, this batch goes here, this batch goes here, this batch goes here. And then when you ship it to Europe, the guy in Europe is going to sell it on the website. He'll sell it to somebody in Thailand who might buy it from him, right? And he'll ship it through postal mail to Thailand. So do you think MAC addresses have any structure? That's not structure. That just tells you, right? Is your MAC address, is it related to mine? And if we don't? Yeah. So are MAC addresses guaranteed to have a structure? If you look at all the MAC addresses of everybody in this room, will we find a pattern? You won't. MAC addresses are flat. Now, IP addresses, do they have a structure? If you look at all the IP addresses of everybody in this room, if we're all connected to the NUS network, will you see a structure? Yes. You will. So what we'll learn, and I mean, yes, this is only network layer stuff, but I like to talk about important things from the beginning, right? So IP addresses, and you already know by just your own experience with networking, IP addresses have a hierarchical structure. So computers that are close to each other, or network interfaces geographically close to each other, have similar looking IP addresses, but not necessarily similar looking MAC addresses. So now can you tell me which one's better? If I have structure in the addressing mechanism, do you think you can build a more efficient network? I think so, right? Right? If you have a flat architecture, then you have to store all the addresses. So that's what we'll find, is that if you have to choose, IP is better because it has a structure. But remember point 8. It's not impossible to use MAC addresses. You can use MAC addresses to build the internet. You just wouldn't want to. Okay, so then the question is, so IP is better in terms of complexity, since IP is hierarchical and MAC addresses are flat. Okay, so now the question is, why don't we just use IP? Right? I mean, so do you see the logical thought process? We have the problem, we look at what's necessary, what's needed to solve the problem, we look at the two options we have, and we come up with a winner. IP is better. Well, so then we're back to, it seems like we've done nothing because we are back to the same question. Yeah?
When you say complexity here, you mean complexity of building a network, not implementing the network.
Implementing routing on such a network.
Not implementing, yes, kind of, but I'm talking more of like from a hardware perspective.
Yeah, from a hardware perspective, because MAC addresses are flat. So how many bits is the MAC address? Does anyone know? It's 48 bits, right? So how many binary vectors of length 48 are there? 2 to the 48. So these are possible destinations. And there's no structure. So your routing table has to contain all 2 to the 48 addresses. And 2 to the 48 is very big. I don't even think like those handheld calculators can compute it. There's not enough digits. Right? It's 2 to the 48 is very, very big. I think, yeah. Okay? So, does that help you?
As in, because you can choose other topologies, like you broadcast everything there.
Huh?
In that case, well, you have collision problems, you don't have this routing table problem.
You can broadcast everything to everybody.
Yeah,
to all 2 to the 48 nodes. Actually, that's not a crazy idea. Yeah, on one hand, that's not a crazy idea. But yeah, so there are other solutions. But if you want to implement the current internet with routing, you'd have to, your routing tables become very unmanageable, right? Whereas with, like we'll see with IP addresses, your routing tables can be very small because of the structure. Okay, so we're back to this question. If we, again, we need we need one, IP and MAC both will do. IP is better from a complexity viewpoint. We're back to the question, why do we still use MAC? So anyone know? It feels like we've just gone nowhere. But I hope I hope you've learned something about, right? So the reason I'm doing this is, in solving all problems, you should be asking questions. Okay, and thinking things through. Many times I help you ask these questions, but I hope to teach you, help you learn to ask your own questions. Yeah.
Basically, the IP address, if without the help of MAC address, the IP address won't just be there, because
So IP address is not enough.
not saying not enough. Of course, IPv4 is not enough, but if you are using IPv6,
So IPv4 is not enough. You're saying, we're not asking not enough addresses. I'm asking, can you build a network?
for now, yes. But I mean, the size is not the case.
Yeah. So you're trying to say there are more MAC addresses than IP addresses, and somehow.
This one is not the reason.
Okay, then tell me.
So basically, because you want IP address, because you want it to be hierarchical.
Yes.
So if you want it to be hierarchical, you have to have some mechanism to distribute the address.
Okay.
So basically, that's how MAC address.
So MAC address is used to distribute IP address.
Yes, somehow.
Somehow.
Yeah,
I don't think it is. No, it's not.
Let's say in DHCP.
But MAC address doesn't have to be used.
What?
No, I'm saying there's no reason you have to use the MAC address to do DHCP. DHCP is a network layer protocol. It works at network layer.
But before the device even have an IP,
Yeah.
there have to be some mechanism to identify the hardware itself.
No. Broadcast. DHCP works by broadcasting.
Yeah, but by broadcasting, yes, sure, but then how the device, the hardware itself be identified?
Yeah, but it's not. You authenticate. Correct? When you connect to NUS network, what do? You sign in.
But DHCP does not come with that.
But it can.
Yeah,
Why
you
not?
can,
Absolutely. Why can't DHCP sign in? It can give you an IP address, and it can make you go to a login page. And the NUS network does exactly that. If you look at the
but that's not necessarily a part of DHCP.
sorry.
That's not necessarily a part of DHCP.
Correct. But so that's why. So you talked about identification. DHCP doesn't identify. DHCP just hands out an IP address. So what you're talking about is how things are done, and I like that you understand how things are done. That's very good. You in this case, and also I've talked to a few other people, and many people will tell me. So I think some of you are thinking this. IP address helps you go like long distance, and then MAC address is used, in a local area network. I think many of you will say that. But that's just, again, how it's used, not why we do it that way. Okay? So the fact is, you can build a completely functioning network with IP addresses. You don't need MAC addresses. So you got to believe that first. Right? You're going, what you're saying is sometimes networks do MAC address filtering. Right? They will, but that's just an example, right? Because we have it. I'm saying you don't need it. Okay, so so the way to understand this is, okay, how is the current internet architected? So The way to see it is, think of a local area network and an Ethernet. What can you tell me about Ethernet? Something you learned in the first half of class. What kind of medium is it? What kind of medium is the Ethernet? Yeah? Multiple access is there. So what kind of medium is Ethernet? What makes Ethernet unique? Yeah, it's a broadcast medium, meaning if we are all on Ethernet, if I transmit something or if I download something, you'll hear it too, right? So let's take an example. Let's take the three of us. You, what's your name? A bit louder. Christina, are you surprised I called on you? Yeah. Why? And your name?
Adrian.
So Adrian, Christina, and I are on an Ethernet. Okay? And I'm, downloading something. Christina is downloading a movie. You're doing something, Twitter or whatever. Now, you have to think, okay? So remember we talked about the protocol stack, right? So let's say we're all downloading something. So that means stuff is coming in from the internet onto our local area network, right? And what does my network card have to do? It's seeing all these packets. It's seeing Christina's packets, Adrian's packets. What does my network card have to do? Yeah, it has to check, is the destination of that packet me? If it's not me, what do I have to do? Drop it, discard the packet. If it is mine, I have to accept it. So does anyone have an idea of why we use MAC address to do that? So the fact is, the MAC address is used to do that. That process is done by using the MAC address. That's a fact. I think that's what I'm trying to say here. I think. Yeah. Okay? So this is the way, this is the how. Did you know that or not? So IP address is used to do routing to figure out the next hop. But in every hop, because every hop is part of some local area network, right? In every hop, the addressing is done by, the next hop is figured out by network layer, but then the next hop's MAC address is also found out. Do you know how? Do you know what protocol gets MAC address from IP address? ARP, Address Resolution Protocol. So on every hop, so remember, network layers figures out the next hop. But what's actually done next is the MAC address of that next hop is computed or determined. It's put into the packet and broadcast onto the Ethernet. And the hope is that only the node that it's addressed to will pick it up. All other nodes will discard. Right? That's how the current internet works. So can you tell me why we use MAC address to do that step? So first of all, could you use IP address to do that? Yes or no? And yes, of course. Because I said you could already build, we already established somewhere up there, you can use only IP address to build a functioning network. So yes, you can use IP address to do it. Then the question is, now we boil down that big question into one question. Why do we use MAC address to do it? Huh? Legacy, no. Close, maybe. I don't know, but thanks for speaking up. Why do we use MAC address to do it?
Is it simpler in some ways?
It is, but can you elaborate? It is simpler. Elaborate, though. So, good. I mean, good. Brainstorming is good. Just because I say no, I'm not shutting you down. I'm just saying let's not go down that route. So again, Christina, Adrian, and I are on a network, right? Let's say instead of 3 people, it was 10 people. That means, and let's say traffic is uniformly distributed. then let's say like what we're downloading is uniform. Then what fraction of packets are actually mine? If there's 10 people. 1/10, right? So what do I have to do with 9/10 of the packets that I see? So to give you a hint. Why we do it at layer 2 instead of layer 3? Yeah. Yes, it's purely for efficiency reasons. Because layer 2 can drop the packet faster than layer 3 can. Because to get to layer 3, you've got to go through layer 2, right? So even though that's a small, you might think it's a small gain, it's applying to most of the packets, right? You've got to reject most of the packets. So you get it? It's a bit anticlimactic, yeah? Yeah, Ethernet is broadcast. No, Ethernet is broadcast. Wireless is broadcast, right? I mean the wireless medium is broadcast. In fact, even Wi-Fi, there's a algorithm that you use to compete for the channel. So initially everybody sends, right? And you compete, and somebody wins. Yeah. So this is what happens. This is how the current internet is built. The Ethernet is a broadcast medium. Now, you make a good point. Why not change Ethernet? Yes, and that is what this gentleman said. That's legacy. Why is Ethernet broadcast? Well, it takes a lot of effort to coordinate, right? So Ethernet uses what? What's the algorithm that Ethernet uses at the MAC layer? Yeah, CSMA, right? It basically listens and sees is anybody transmitting. And that's only possible if it's a broadcast medium. Otherwise, you would need to have coordination. You would need to have like a central controller assigning time slots. Yeah, so Ethernet is broadcast, but you're absolutely right. You could design another mechanism. Okay? So, yeah.
So you said that you need to have both MAC and IPs because of efficiency.
I didn't say you need it.
Like right now we have it because of efficiency.
Yeah.
But my question
No. We use it because of efficiency.
My question is, but because of that, every data packet that's going out now has both MAC and IP.
Yeah.
Like overhead. So does it actually
This is a good question. So the reason I bring this up, the reason we're talking about this is that yes, the next generation of network design could be different, right? You might think about reducing header space, right? Maybe only having one addressing mechanism. Yeah, I mean, so this is what the next generation of network designers, which are you guys, hopefully will have to tackle. That's my point, right? That's why I keep asking why all the time, right? That's why we're trying to answer this question, not because the final answer is like, whoa, it's a bit anticlimactic, right? Because it's for engineering reasons. It's a bit more efficient to reject that layer 2. So just to summarize, I think I should have it here. If not, I'm telling you. Okay, so the answer is, yeah, because I have to reject most of the packets, it's more efficient faster to reject at layer 2 than at layer 3. Right? Yes?
It's perfectly okay to put the IP address into hardware and make it work in layer 2, right?
You could do that, yeah. So this is a great point.
All those high performance they do that. They use the FPGA to do it in hardware.
Yeah. No. So you could absolutely allow. So remember, the protocol stack is it's in software, right? So every layer.
It's just a model.
No. All these protocols are function calls, right? They're just function calls. So there's no reason why you couldn't allow a layer 2 function to read a layer 3 address or layer 3 header information. But the question is, why would you not want to do that? There's a reason why you would not want to do that. You could do it, but there's a reason we don't do it. Do you know? Because you violate the layering principle.
Yeah, I'm saying why the layer is there in the first place. Of course, the model is there. It's
Yeah.
also for the legacies, but
Yeah.
why can't you break it?
So you can break it, but then you have to ask the question, why don't you break it? You don't break it because of the benefits of layering.
Yeah, I mean, if you put in that argument of the efficiency, or you just want to use IP, then I mean the layering itself doesn't need to be in the.
Yeah, because like you forget that when you have a standard, right?
Yeah, but the standard itself is a legacy.
I'm not saying a legacy standard. I'm saying having a standard.
Yes.
Having a standard is necessary so that different companies can make devices that talk to each other. For example, this is IBM laptop, right? Lenovo, right? Your Lenovo laptop with its Wi-Fi chip in there, made by, I don't know, probably made by TSMC, can talk to Cisco.
Yeah, sure.
How is that possible? Let me finish. It's possible only because there's a standard.
Yeah.
So,
But the standard does not need to have all the details. I mean, not saying the details have to be in that layer.
what you're saying, I know what you're saying. What you're saying is, why not just allow this because it's so good? Yeah? You're saying I can make it so efficient, why not allow the link layer to read the IP address and reject? Correct? That's effectively what you're saying.
Yeah, if you say so.
No? That's not what you're saying?
I'm saying the standard.
Yeah, that's what I'm saying. Why not change the standard?
Yeah.
Yes, that's what you're saying. Am I paraphrasing you correctly? But now, there are 100 people saying, hey, here's my proposal, and my proposal, and I have 100 proposals. Which one do you choose?
I mean, that's how the IEEE meetings are done.
Yeah, so, and that's, you're absolutely right. The IEEE meeting said I can't choose 100 proposals. Because if you have 100 violations of a reference model, then nothing works. You see? So if you have a standard and everybody follows it, everything works. But if you have a violation of it, if you want to evolve it, you cannot. You got to make sure your interfaces remain the same. So everything you say is possible, but it's a matter of degree. If I allow one proposal, why not one of 1,000 proposals? And then suddenly everything's a mess. This is why you don't violate layering. But that being said, there are proprietary systems that do. There are proprietary systems that violate layering. One good example of that is wireless. Like next, we're going to talk about transport layer. Transport layer has to do with end-to-end reliability. And one of the things that a node does is it tries to sense congestion in the network. This is transport layer function. If there's congestion, that node will back off. It will say, I will put less data into the network because I'm sensing it's congested. Okay? Now, if you're in a wireless scenario, you're driving in your car, you go behind Marina Bay Sands, you go into a deep fade. The building is blocking your line of sight to the access point. You're going to go into a deep fade. Well, you're going to start dropping packets because you're in a deep fade. What's your transport layer going to think? There's network congestion. And it's going to back off. But the next second, you're out of the line of sight of Marina Bay Sands. You're out of the deep fade. But as we'll see in transport layer, it will take a long time to recover. Because transport layer is very aggressive when it senses congestion and is very conservative in building back up. So in that situation, there are proprietary systems that do the following. They give the transport layer access to the physical layer. Physical layer is where channel estimation is done. So if the transport layer can see, oh, there's a packet drop, possible congestion, but oh, I'm in a deep fade. Oh, I'm not going to back off like I normally would. Yeah, so you can build in cross-layer mechanisms, and people have done that, but for proprietary systems. Right? It's not in any widespread systems. Okay? So this is a good point you make. There are solutions, and yeah, you can choose as the network designer of the next system to build in some of these. And that's precisely what I'm trying to sort of, why we are asking why. So that you can see what the considerations are, and then you can exercise your, design judgment when you're designing your own network. Okay, so I think we've put this to rest. Okay? So you should be able to articulate kind of a story, right? Why we use MAC and IP on the current internet. Okay, and I hope that the series of questions get you to think. All right, what I want to do next, so I'm very disappointed because I want to do Wireshark stuff, right? All of you have installed it, I hope. If not, install it now. Go to wireshark.org and download it. I want to install it on here, but I couldn't do it because of administrator rights. And even after I got administrator rights, I still couldn't do it. So they gave me the wrong, they didn't give me proper access. So I'm gonna pull out my laptop and we'll do Wireshark from there. Okay, so if you remember last time we talked about ping and traceroute, right? Yes or no? Right, ping and traceroute were the two tools that kind of let us do some, let's say, run some network functions, right? So what I want to do now is run Wireshark and show you live a little bit about Wireshark stuff, okay? Okay, so actually I realized something. Before I do this, I should probably did we talk about Wireshark last time or not? Oh, then I better talk about Wireshark. Sorry about that. I forgot. I thought we'd done this. Okay. So what is Wireshark? Wireshark is a packet analysis tool. Okay, it's a packet analyzer. Okay. So it basically allows you to look inside the packets flying around your network. Okay. All right. So who uses these packet analysis tools? A few people. System administrators use it. Okay. Good guys use it, and bad guys use it. Okay. So don't do this. Everything that's here under the malicious individuals, you should not be doing. This is going to come up like 3-4 times, so bear with me. I have to make sure, okay? Because, so who likes Spider-Man? Like, I'm a huge fan, right? So who knows the story of Spider-Man? Like, do you know that he had an uncle? Yeah. Uncle what? Uncle Ben? Right? And what did Uncle Ben tell Peter Parker? He told him something. With great power comes great responsibility. All right, so I'm going to endow you with some power. Let's not argue about how great it is, okay? Because you may be like, this is nothing, right? But anyway, it's a lot of power. So you must be responsible, okay? So we're going to use it for educational purposes, okay? Okay, so it's a packet capture and a packet analyzer. Actually, the packet capture part is a separate library. All right. So this is where it fits in. It basically takes all layer 2 frames, and it saves them. Okay. So for example, I could do it on my interface, but again, back to what is Ethernet? What is Ethernet? It's broadcast. And remember I told you we have to reject packets. I can not reject packets, right? And that's where the bad stuff comes in. You want to crack your own password? Go ahead. Right? Collect your own packets, you're doing that anyway. But you collect other people's packets, don't do that. And try to do something bad with it. Right? Here we're actually going to capture those packets. And wireless is a, what kind of medium? Broadcast medium, again, right? The same thing. Okay? So it takes all layer 2 frames. So like for example, this NIF right here, this is Wireshark, is running here. Basically, you can connect it to a hub or to a switch, and it will just capture all those packets. Okay, so Wireshark is a free open source packet analyzer. It knows like every protocol, right? I mean, they update it. Any time a new protocol comes, it's updated. It used to be called Ethereal. So if you know anything about this or have used it in a previous life, the same tool used to be known as Ethereal. Okay. Okay, why do we use Wireshark? Administrators use it to troubleshoot and debug network protocol implementations. You can use it to detect network intrusions, right? If you see a certain pattern of IP addresses, you can use it to make an inference that you're being attacked. And don't do the bad stuff, okay? Because it's possible for you to do it, right? I tell you this, I'm not revealing anything to you. If you just play with it a bit, you will see what is possible, okay? So remember, when you join the students, you sign the acceptable, like a computer use policy, right? You signed that, right? You did, otherwise you wouldn't be sitting there, okay? So you did. All right, so spying on other users, trying to crack people's passwords is in violation of that, right? So you don't come to me later and say, hey, my prof told me I could do this. No, your prof told you at least 3 times now, don't do this. Okay, I really don't want to get you caught. And, you know, he's laughing, but meaning I don't want you to do bad stuff. Okay, I'm going to watch what I say around you guys. Okay? Just don't do bad things, okay? Okay, I mean, we're just like, the point of us doing it is so we can learn about networking, okay? All right, so yeah, so Wireshark sits here, right? The packets, so the packet capture can be either in Windows, it's WinPCAP. In Linux and in OS X, it's libpcap. And Wireshark is a packet analyzer. Now, Wireshark ships with a packet capture. So actually, when you install it, that's all you need to do. It ships and installs both the capture as well as Wireshark. I think when you install Wireshark, it asks you on Windows if you want to install WinPCAP. I don't know why it asks you. It already installs it. So has anyone installed it on Windows? Did it ask you? Oh, okay. Did you hit no or yes?
Yes.
Oh, okay, it's fine. I think if you hit no, it would still work. Huh? The loopback NPCAP? Because I don't have Windows, I don't know. On OS X, it doesn't ask me anything. But I think you shouldn't need to install anything. From my understanding, you don't need to. That's why I wanted to install it here, so I could have a Windows version of it, right? But I died. I couldn't get the admin privileges thing, okay? But don't worry, I'm going to get them to just come and install it because I want to run it here. I don't want to always have to keep pulling up. Okay, so what I'm going to do is, so for the rest of this slides, I have some slides on the interface, but I'm going to just show you live. Okay, so this is running Wireshark. Okay, so you can install it from wireshark.org. Okay, you can get whatever version you want. There's also a portable version. Like I may have to resort to that to install it here. The portable version you actually don't install. You just run off a thumb drive. but I haven't got a chance to put it on a thumb drive, okay? So if that's what I have to do, I'll do that for the Windows case. But what I'm going to do now is let us run this thing. Okay, so to show you I'm running it. So the interface should look almost the same. Can you run it and help me? Does it like when you run it? Oh, sorry. BGA. Okay, so I'm going to just run it. So what did I just do? Oh, I ran Excel. Okay, so I'm going to run Wireshark. Is this what it looks like when you start up? On Windows?
Yeah.
Okay.
Have other things underneath.
Okay. So what you have to do here is you can do two things at startup. Or you have to do one thing and the second optional thing. One thing is you have to choose a network interface. Now I'm connected to the wireless network. You can see up there. Okay, so right, I'm connected to NUS here. Okay, so I'm using my wireless interface. So I'm going to select that. Okay. Now I could have also chosen my Ethernet interface. Now I have a whole bunch of other interfaces, but I'm not going to worry about that. The second thing you can do optionally is use a capture filter. A capture filter says, I'm only going to capture certain packets. Okay? So Wireshark has another type of filter called a display filter, which means of the thing I've captured, I want to display certain types of packets. So you could, in the worst case, just capture everything and then display what you want. But that's a bit overwhelming. So sometimes you decide what you want to capture and just capture that. And then you can display some subset of that. Okay? So remember, there's capture filters and display filters. And here at the top, you can specify a capture filter. So initially, I'll put nothing. Okay? Okay, I won't do a capture filter. So we see that there's a ton of things happening, okay? Right, and most of these are, I don't know. This really makes me wonder. Oh, Dropbox. Okay, so all of my, I have all these little, network storage applications running, cloud storage applications, and they're all sending some packets and stuff. Okay, so okay. Anyway, I just wanted to show you that. Let's rerun Wireshark. Let's check my Ethernet interface to make sure there's nothing there. I mean, there's nothing plugged into my Ethernet interface to show you that when I run that, I should get nothing. I hope. If there's something there, it's like a ghost protocol. Okay, so this is good. Nothing being captured. So let's go back to the wireless, okay? But let's do this. Let's just capture, so web browsing uses HTTP. So let's see if we can capture just HTTP packets. Okay, let me see if I can figure out how to do that. So Wireshark capture filter HTTP. Okay, so just to, let's see, to show you that it's not that difficult, that you can also learn how to figure stuff on your own. So if I want, like, okay, I can, for example, let's capture just DNS packets, okay? Let's see what that does. Oh, shit, hang on. Sorry. Okay. Okay, so DNS runs on port 53. Let's do that. So right now, there should be nothing. But when is DNS used? When I go to a website, right? So let's say I go to Chrome, and I go to stanford.edu. Okay, so like you probably don't know this, but every time you type a website into your browser, there's a DNS query that's made. So now, so there's a source. So what Wireshark shows you is on that top you see a bunch of rows, right? Indexed by 1, 2, 3, 4, 5, 6, 7. Each of these is a packet. Okay? Now, what it does is in the different columns it shows me some details, some very high level details. It shows me the source IP, the destination IP, the protocol that's used, the packet length, and some information about that query. Very high level stuff. I can go and click on one of these. So if I, for example, click on that one, then down here, in this area here, I get more detailed information about the contents of the packet. So for example, I get the Ethernet frame information. Okay, so sorry, I get the, now layer 2 has a bunch of functions. Framing is one of them, and Ethernet is one of them. Right? 2 protocols are run. So it breaks it out. There's some framing information. There's Ethernet protocol. The third row is, now there's a arrow by each one, so they're all expand. Okay, I get the Ethernet, sorry, I get the layer 2 frame, the layer 2 Ethernet, layer 3 network layer protocol. Then I get the fourth column is UDP. This is transport layer. And then I get the application. Okay, so this is, if you go and you were to break it down, it says here, it tells you some framing information. All the information here is used to do what is done at layer 2 in terms of framing. So things like synchronization and all is happening here. Okay? The MAC address is here in the Ethernet. So MAC address is not part of framing. It's part of the medium access control, part of Ethernet. Okay, and we see there's a source MAC address and a destination MAC address. Okay? Then there's the network layer. So this is IPv4. Now, if you look at it, there's also a source. So notice that this matches. So the source in this packet is 172.23.75.183. So that matches, right? It's this information here came from here. Okay, so this is nice. And the destination is 8888. Does anyone know what 8.8.8.8 is? Yeah, it's Google's DNS server. So I find it very fast. So I use that instead of the NUS DNS server. Okay, so I'm sending a packet from me to the DNS server. So let's make sure that's me. Oh, wait, hang on. Can you see? So on Windows, it's ipconfig. On Linux and Mac, it's ifconfig. So this just shows me all the network interfaces. If I go to EN1 and look at the internet address, that's my IP address on the wireless network. Okay, and does it match? Does it match this? Good, it matches, right? So I mean, this is easy stuff, but at least when things are working out and you can understand, it makes you feel good. You can move forward with harder stuff, right? So we're just checking that the IP address matches. The 8888 is actually the DNS server run by Google.co. What about MAC address? My MAC address is right here. It's called Ether. MAC address has a few names. It's called sometimes called physical address, Ethernet address, or MAC address. Okay, here in this interface they call it Ether address. So can we double check that this matches? So the MAC address of the source is right there. Does it match mine? 7056.81 colon 95.65.6f, right? So we're, okay, so this packet is sent by me, right? So at the network layer, we saw that at the network layer, this is my IP address and this is the DNS server IP address. At the MAC layer, we see that this is my MAC address and this is the MAC address of the Google DNS server, right? Right? You probably have figured out that I have a tel. Do you know what it means to have a tel? That there's a sign. Whenever I pick up my bottle and I'm going to take a drink, it means you should be thinking. So, is this the MAC address of Google's DNS server? It's not. So what is the MAC address of? Yeah, it's the MAC address of the next hop. The way to sort of understand that with what you know is that network layer is end-to-end, has a view of the entire network. MAC layer doesn't. Link layer is not end-to-end. By the way, this is another challenge in building a network with MAC layer addresses. You need to advertise them, right? You need a service that can map. So what's a service that maps friendly names to IP addresses? DNS, exactly this, right? There's no service that maps friendly name to MAC address. You'd have to build one. Okay? So we see that. Let's see, what else do we see? There's a whole bunch of things at the network layer, a whole bunch of header fields. So like this is your first look inside the header fields, right? You can see that there's a ton of stuff happening, right? You can see that there's things like time to live, there's fragment offset, a whole bunch of other things that allow protocols at the network layer to do something, to carry out some tasks, to offer some service. Like for example, you see differentiated services field, right? The network layer right now has the mechanism to offer differentiated services based on, some a category of service that a customer may have bought, okay, that may have purchased, okay. So that's the network layer. A transport layer is here. Now, what this tells you is that the transport layer, we're using UDP. When we talk about transport layer, we'll see that there are two broad classes of transport layer protocols, TCP and UDP. UDP is a transport layer protocol with no reliability. TCP is where all the reliability comes in. But it's there for services like this that don't really require any reliability. For example, if your query to the DNS server gets lost, you'll just send another one. So you use UDP because you don't necessarily want acknowledgement for your DNS queries. Okay, we saw an addressing mechanism at layer 2, which was the MAC address. We saw an addressing mechanism at layer 3, which was IP address, and there's a source and destination at transport layer. It's called source port and destination port. So there's an addressing mechanism at the transport layer. Okay, so when we get to transport layer, we'll discuss what that addressing mechanism is used for. Does anybody know? So both MAC and IP address address a network interface. What is port address? Does anybody know? What? What does it address? Yeah, different kind of service is good. Can you be a bit more precise? There's a more general term. It addresses a process running on a host. Okay, some people might say it addresses an application. Yeah, except an application can have multiple processes. Like Chrome can have multiple tabs. Each tab can be doing something different. Okay, so it's a port addresses a process. A process is the fundamental quantity that consumes and generates information. Okay, so we see that at the transport layer, there's some information, and then we can look at the network layer. At the application layer. So DNS is an application layer. So we see that. So some query. I mean, you look in here. Yeah, I mean, so we'd have to go read a little bit more about how to dissect this here. I was kind of hoping to see Stanford here, because that's what we did, right? We looked at. So someone, interesting. It went to gstatic.com. Oh, the Stanford query is actually here. I don't know what gstatic is. Anybody know? Yeah. This is interesting because this is not. So the actual query to Stanford is here. And you can see in the query, there's the actual query that the DNS server is going to respond to. And then it will respond to you. So notice that the source here is me, the DNS server is here. The next response is the DNS server is the source, and I'm the destination. And in there, you should see the answer. So somewhere in here, you should find maybe it's here. No, yeah, so I realize what's going on. So a lot of companies, they want fast response. So what they do is they maintain cache, caches around the world. And here you notice that it's redirecting to, if you look down here, this went down here, it's redirecting to Amazon AWS. So I think they're running a local cache, which is why I'm getting redirected there. So this is interesting. You wouldn't actually know that unless you dissect this, right? When you go to a web browser and just do stanford.edu, you just see the website. But actually what this is telling me, this is my guess, I guess we can investigate further, but it's actually redirecting us to a different, to an Amazon, to a cache running on Amazon AWS. Okay? Okay. So this is all just with capturing DNS query. You could do the same thing with capturing HTTP packets or whatever you want. As I mentioned up here, you can also put in a display filter. So this is after I've captured a DNS packet. Let's see how to do a display filter. So like, for example, maybe we can do this. So just show me all my queries to, right? So I can say where tell me where the destination is 8.8.8.8. So this is all the queries that I'm sending out to the DNS server. Okay? So right, so capture filter limits what you capture. Display filter limits what you show from what you've captured. Okay? So any questions? It's very blinding. Okay, so what I'm going to do is throughout the semester we'll play with Wireshark. Okay, I may right now I don't have any assignments. I'm not giving you any homework beyond install Wireshark and at least carry out some of these things that I've done in class. Okay, it'll be useful for you to figure out what's going on, get your hands a little bit dirty. Okay, rather than networking feeling like it's just theory, you're actually going to go and dissect some packets and see what's going on. Okay, what would be nice is if you looked at all of the different layers and looked at all of the fields there, right? And said, oh, okay, there's this field. I wonder what it's for. If you're really interested, go Google it. But we'll talk about most of those fields, at least at the network and transport layer, right? At the layer 2, you should have already done that. You should have already talked about what the different fields are. Okay, so any questions about this? Okay, so what I'm going to do is we're going to start. In case you're interested, there's a set of slides here, which before I started doing Wireshark Live in class, kind of put everything together in terms of what the different fields are at all the different layers. Okay, so you can take a read through this and just get a first view of what the different fields are. This is just cut from the Wireshark output, okay, but in slide form. Okay, so what I want to do is I want to start our discussion of transport layer. Okay, transport layer is, so we're going to talk about 2 layers, layer 4, layer 3. Layer 4 is transport, layer 3 is network. Which is coming up. Okay, so we'll talk about transport layer. We're going to just start. Okay, we'll really pick up transport layer on, now in terms of Mondays and Wednesdays, I think in your, in the timetable it says lecture and tutorial, right? I'm not going to make a distinction. Okay, we're just going to continue. All right, is that good? Okay, so we'll solve problems when we need it, and we'll talk about ideas when we need it. Okay, so transport layer, I'll talk a little bit about the principles that underlie the transport layer. The main thing to keep in mind is that transport layer is responsible for end-to-end reliability. And what you should do is in every single function that we talk about, you should ask the question, how does this support end-to-end reliability? Because that's what it is. Now, sometimes you'll be able to do it, and sometimes you won't. And then what you found is a function that's just put there. Because functions need to be put somewhere, right? And sometimes they are put in a layer even though it's not the main job. So that's why I say the main job. Okay, so we'll see that sometimes some functions, like for example multiplexing, is not really about end-to-end reliability, but all the others are. Okay, and then we'll talk about UDP and TCP. And again, just to let you know that I'm using slides and graphics from Kuros and Ross. Right, this was the book that I recommended to you. Okay. Okay, so transport layer sits between the network layer down here and the application layer up here. Okay, and so I want to use this slide to figure out. So every layer, in some sense, forms a virtual connection between that layer at the sender and that layer at the receiver. It forms a virtual connection. Why? Because whatever the network layer header, the network layer at the sender, whatever it puts in the header of the network layer is what the network layer at the receiver will read. So it's like a virtual connection, okay? So application layer is a connection between 2 applications, right? That makes sense. Transport layer is communication between 2 processes. Now, in your class, you have to do a lab, right? You have to build sockets. So that's what you're doing. You're building a transport layer connection. Okay? So a socket is a process, indexes a process. Okay? So the transport layer is a communication between processes, and the network layer is sort of logical communication between, I wrote nodes, but technically between network interfaces. Okay, so 2 network interfaces, the network layer connects. Okay? So we're going to talk about these 2, but in this set of slides, we'll talk about the transport layer. Okay? So a transport layer, as I said, gives you a logical communication between 2 processes. Of course, so transport layer is end-to-end, so it's running on the end hosts. right? So does a core router on the internet, does it implement the transport layer? No, it doesn't. Okay, because transport layer is end-to-end. Okay, so the state, the interior state of the network is not kept by the core routers. Okay, only the edges. So we'll see another idea. Maybe, so at the end of this, I'm going to, so there's a very important principle here called the end-to-end principle. Right? It says that intelligence exists only at the endpoints of the network. And this was a major design principle of the internet. Okay, and later we're going to question it and say, why? Okay, can we do better? So I'll leave that for later, but we're going to question this end-to-end. But right now, the fact is transport layer is end-to-end. So we call, now we use the word packet to be generic. But actually, in networking, we call each of the packets at every layer, we give it a name. So application layer, the packets are usually called messages. Transport layer, segments. Network layer, does anybody know? Huh? Packet is the generic term. It has a name. Datagram. And then link layer, frames. Okay, so if we ever use one of these terms, you know what layer I'm at. If I use packet, you might not know unless the context tells you. So don't be too worried. Sometimes I'll use packet, but it should be clear from context. Okay? Right, and on the internet we use TCP and UDP. Okay, these are the two broad protocols implementing transport layer. Okay, so the transport protocols, as I mentioned, are UDP, which is User Datagram Protocol, and TCP, Transmission Control Protocol. TCP is sort of the heavy protocol where the heavy lifting for end-to-end reliability is done. Okay, so things like you set up connection, you look for error in packets, you discard corrupted packets, you retransmit lost packets, you do flow control and congestion control. UDP, on the other hand, is like a placeholder. Because of the reference stack, you need something there. You need an interface. Let's say you want to do nothing. You still need the interface. And UDP is that interface. It does nothing. It doesn't do any end-to-end reliability. Actually, it does some error checking. So maybe not fair to say it does nothing. But it does mostly nothing. It does some error checking, and it does multiplexing and demultiplexing. Okay, and transport layer has no other guarantees. In fact, statistical multiplexing should tell you, because we're using statistical multiplexing in the whole stack, there are no guarantees. No bandwidth guarantees, no delay guarantees. Okay, it's all what's called best effort service. Okay, so why don't we do this? We'll get one function out of the way really quickly called multiplexing and demultiplexing. So on the right here is the anatomy of a TCP or UDP packet. Now I'm only showing you the things that are necessary and important for multiplexing and demultiplexing. But this is our first look at what I call the anatomy of a packet. Okay, what we're going to do both for network layer and transport layer is we're going to take our data and we're going to look at it in 32-bit chunks. Okay, and then we're going to stack it. Right, so from left to right there is 32 bits. Okay, and the first thing that's in the transport layer header is a source port and destination port, each of length 16 bits, right, which makes up 32. So it turned out that many things are on 32-bit boundaries. So this stacking up in 32 is quite convenient. Okay, you don't need to do it like this, but I do it like this because it's nice to like visualize. Okay, so so all we need for multiplexing and demultiplexing is a source port and destination port. And I put all of the other header fields and the application data is all there. It's just masked because I don't need it for this function. So this function is implemented in transport layer, but it's not for end-to-end reliability. It's there because it needs to be there somewhere. Okay? What this essentially does, remember the port number addresses a process. Now, can you think, why do you need to address a process? So here's my computer, okay, and there's the Ethernet port, and I have a cable plugged in, and now network layer can send packets out and can receive packets. Is that enough? Like, is that enough? Can you think? Like, there are a whole bunch of applications running, right? There's my email client. I have my Chrome browser with multiple tabs. One's watching a movie, one's on Twitter, one's on Facebook. They're all generating packets, right? And all those packets have to go out this network interface. What do we call that function? You've probably seen it in your digital design classes, right? What do you call when all the different applications go out one point? There's one wire here, and they're all put on that wire. Yeah, that's multiplexing, right? So that's the first step. Things have to get sent out a network port. It could be wireless or wired, it doesn't matter. Okay? If we look at just the wired, there's a multiplexing of packets from different processes happening. Then what has to happen on the reverse link? Yeah, right? When Chrome tab 1, the data meant for the movie running in YouTube in Chrome tab 1 comes back, it has to make it back to that tab. When my email packet comes, it has to make it to my email client, right? So a demultiplexing has to be done. And now having a network address is not enough, right? Because it's the same reason why having, maybe when you live at a house, having your address is not enough to get a packet to you. I also have to put your name on it, right? So your name and your address are actually technically your full address. In the same way here, if I want to address a process that's running here, then I have to address it explicitly by the port number. Okay, so every process, when you start it up, on Windows, on Linux, on Mac OS, any operating system will have a will have a process ID. And for networking, it will have a port number. Okay, and that process will listen for packets whose port number is the one assigned to it. Now, some port numbers are kind of reserved, like 53 is for DNS. So you'll never see an application use port 53 except DNS. 22 is SSH. I think 15 is, does anyone know what port 15 is? I actually forgot. A lot of the low number ports are all reserved. Is it Telnet or FTP? Yeah, and then there's a port 80, for example, is for HTTP. Okay, so so most of the higher number ports are what's used. So when you, like for example, if I was to, I don't know, I'm going to put myself on the spot here. What's the process manager in Windows? Can I do Control Alt Delete? Yeah, Task Manager, right? Whew, I remembered that. It's been a long time. Hang on. I can't say anything. More details? Okay, PowerPoint. Can I see a port number? Oh, it's still there? Oh, that's where? Ah, sweet. There's a process ID here, but for the life of me, I can't figure out what the port number is. Anyway, it's there. Just I'm going to find out on Windows. It doesn't expose it to you. Okay, but sorry, these may not be networking, but for example, if I was to look at Chrome, I'm running Chrome, right? Wait, I'm not running Chrome. Let's run Chrome. Yeah, I'm not sure. It should be there somewhere. There's a process ID. So this process ID is probably tied to the port number. Okay, so yeah,
Under the task manager, you open resource monitor. Under processes, you should be able to find resource or performance.
which one?
Performance under performance. You have resource monitor. Bottom right, bottom left.
This one? No, let's see. They actually gave me this thing, but I told you it didn't work, right? No, I don't know what it is. Anyway, you're saying that it's here?
Yeah, it's there.
Okay, cool. So you can get the port number?
Yeah.
Okay, cool. So let's go back to this. Yeah, so we get the message, right? So the way to look at it, and this actually will come in very useful. I want you to remember this when we talk about network address translation. Because network address translation is an example of layering violation. Because the network layer is going to read a transport layer header because it's the same exact function as multiplexing and demultiplexing. Okay, but it'll be done at the network layer. Okay, so just remember this idea from transport layer. It uses port number to address a process. Okay, so that's pretty much it. So this function, once it's done, we never need to speak about it again, because it's just implemented here, and it's used to take multiple packets from multiple processes on the same output network interface and reverse that process. Okay, so I think, let me see, I think I'm going to end here. Okay, so I'm going to end here. Okay, when we come back on Wednesday, we'll continue talking about transport layer, and what we'll do is we'll put UDP to rest. Okay, so multiplexing, demultiplexing, and UDP are two simple things. We'll finish them and then do the heavy stuff, TCP. Okay, thanks. If you have questions, I'm up here.